Okay. So in the last lecture, we defined what is the blockchain formally. So today we are going to, construct a really simple blockchain, right? We talked about how to construct a blockchain from Byzantine broadcast last time, but this is not really the kind of protocol you want to implement in practice. So, blockchain is the modern new name, right? And the name was coined because of Bitcoin. And what is a blockchain? It's a chain of blocks. And a block is kind of like a batching technique, right? A block is used for batching, and because typically you don't want to confirm transactions one by one, you batch them together and put them in a block, and then you chain these blocks together, and that's why it's called blockchain. But blockchains actually have been around for a really long time, even though cryptocurrencies kind of popularized this term blockchain, right? So as we said, classically it was called state machine replication. So for the purpose of this course, state machine replication and blockchain mean the same thing. And companies like Google and Facebook, they have been deploying state machine replication for a long time because everyone needs to replicate their computing infrastructure. You don't want to run your Facebook credit or Google wallet on a single server, because if the server crashes or anything, you are in trouble. But once you start replicating your machines, consistency becomes a big challenge. Okay, so actually, before I talk about today's protocol, right, today we are going to construct a really simple blockchain protocol called Streamlet. So that's what we are going to talk about today. But before that, I can talk a little bit about the history of blockchains, right? So essentially, classically, the classical style protocols are represented by PBFT and Paxos. Like, you may have heard of these names. And there have been a long line of works that try to improve these protocols. So there are many variants of PBFT and Paxos. And for a long time, such state machine replication protocols, they're known to be quite complex and difficult to understand. So in particular, there has been a line of work that's just focused on making these protocols simpler, right? And then there are actually well-known works like, Paxos Made Simple, the ABCDs of Paxos, RAFT. Okay. So that's the classical line of work. And then what happened was, okay, Bitcoin came around, and that was back in 2008 or something. And the breakthrough idea there is classically consensus was performed in a permissioned environment. What is a permissioned environment? It's a closed environment where the set of consensus players are well known ahead of time, right? Because Google and Facebook are running these protocols, and they can define, this set of nodes are going to participate in the protocol. But with Bitcoin, it's an open participation environment, so often called the permissionless environment. And so these are permission, what we call permission consensus. And then, what's great about Bitcoin is that for the first time, it showed consensus is possible in a permissionless environment, and anyone can join. And what makes it possible to reach consensus in a permissionless environment is this proof of work idea. Because in a permissionless environment, one big challenge is that you can impersonate other people and cast many votes, right? I can impersonate Junxi, Anoop, Shravan, Ke, and I can cast many votes and try to outnumber the honest folks. But with proof of work, it defends against this kind of Sybil attack. Essentially, every unit of computing power you have is like proportional to your voting power. So we are actually going to learn about Bitcoin's consensus protocol later in the semester. But the biggest drawback of proof of work is that, it's very wasteful. It's not green, right? It burns electricity, and the electricity consumed at some point, and this was like even a couple of years ago, was already like as high as the electricity for the entire country, Ireland. And therefore, many blockchain projects, like they start to switch to a new paradigm called proof of stake. So proof of stake is the new paradigm, and the idea is like in proof of work, and your voting power is proportional to your hash power, but whereas in proof of stake, your voting power is proportional to the amount of cryptocurrencies you hold. But the interesting thing is that when you look at proof of stake, like you look at how this type of consensus protocols are constructed, they actually rely on permission consensus. And the point is that at any snapshot of time, in a proof of stake protocol, the consensus committee is well defined. It's clear who are participating in the consensus at any point of time. So you can just run the permission protocol, right? But like with proof of stake, like one challenge is that you need to periodically rotate the consensus committee to make sure it reflects the latest stake distribution. Okay. So, I mean, in some sense, this is great news, right? Because proof of stake like returned to classical, permission consensus. But then the interesting thing is that every blockchain project was like reinventing their own consensus protocol. So you may wonder why, right? Given that, proof of stake built upon classical permission consensus, like why can't we benefit from, all these years of work that we have done? Well, I guess it turns out that these classical protocols, PBFT, Paxos, and the entire family, that they're still pretty complex and difficult to understand. And like one reason that's driving these blockchain projects to reinvent consensus is because they want simpler protocols. Okay, so we are going to actually talk about a protocol called Streamlet, and in comparison with these classical protocols, like it's kind of almost absurdly simple in hindsight. Like the whole protocol is like propose, vote, propose, vote, propose, vote. Like there's nothing else. And then, there's like a kind of cute finalization rule that tells you when you can finalize blocks. And that's like where a lot of the magic happens. Okay. So let's just get to the business. We are going to talk about the protocol, right? Streamlet. Okay. So let me first explain this protocol at a high level, and then I can write down the formal version. So at a high level, what's going to happen is that, we are going to proceed in epochs. So let's say I'm just going to call every epoch 1 second, right? It doesn't have to be 1 second, but for convenience, in this lecture, we're just going to assume 1 second. And so actually jumping ahead a little bit, actually the protocol's consistency doesn't depend on network timing assumption. Like even if the network can be badly partitioned and the honest nodes cannot deliver messages, right? Or like the network delay becomes really long, it doesn't matter, consistency always holds. But of course, when everyone like is in their own island and cannot talk to each other, we cannot guarantee liveness. So the protocol is going to guarantee liveness when network conditions are good. So what does it mean for network conditions to be good, right? So if the honest players can talk to each other, make a round trip within 1 second, which is also the epoch length, then at that moment we start to make progress. So that's why there's this parameter, right? It defines like essentially when the protocol can make progress. And our goal is, let's say, things are perfect and network conditions are good, our goal is to like have a leader propose a block in every epoch, and then people will vote on the proposal. And then when the block gains enough votes, it becomes notarized. So notarized means it has collected votes from 2/3 of the players. Okay, so something like super majority voting, right? So propose vote, and we do this every epoch. And the blocks are going to be chained together using a hash chain, right? So throughout this lecture, we are going to assume, okay, so for instance, this is a blockchain. And if you look at each block, right, let's talk about the format of each block. So we are going to assume every block contains a tuple, H, E, and TX. So this H is like, so in fact, the first block is called the genesis, right? The first block is canonical. So actually, let me just write, the first block is called genesis block. And the genesis block is of the following form. Okay, so then every other block, let's say this block is of the form HETX, and H is like the parent hash. So the parent hash, like essentially, is a hash of the entire prefix. So this entire prefix chain is called the parent of this block. Okay, and then E is the epoch number. So this is the epoch number. And the TX, like, transactions, and that's just like an arbitrary payload string. It can be a set of transactions you want to confirm. Okay, so for a chain to be valid, like we want to make sure every block's parent hash indeed matches the hash of the entire parent chain, right? So let me write down the validity rule. So first, every non-genesis block's hash let's say is equal to hash of the entire parent chain. And then we also want that the epoch number, right? So each block has an epoch number. So for genesis block, the epoch number is 0. So let's say this has epoch number 1. This has epoch number 3. This has epoch number 5. This has 6, right? So we want the epoch number to like strictly to be strictly increasing. Okay, so that's just like a little bit of setup, right? This is the format of the blockchain. And the protocol proceeds in epochs. And every epoch will have a leader. So let me denote LE is the leader of epoch E. And we are actually, like, for simplicity, we are going to consider a very simple leader election policy. Essentially, we will hash the epoch number. And this gives us the leader of the epoch. So in some sense, if this hash function H is random, then we are electing a leader essentially at random every epoch. Okay, so also, by the way, what I want to mention is like, so here we are hashing the entire chain together using a cryptographic hash, and we are going to assume that this hash doesn't have collision. So in fact, I mean, for a hash function, collision exists, right? So the more precise way to state it is to say like a polynomially bounded adversary cannot find collisions. And what this means, right? So if the hash function, like assuming the adversary cannot find collision, then essentially whenever you have a block, it uniquely binds to the entire prefix because of this hash. So in other words, like, sometimes block and the entire chain, they can be used interchangeably because given the block, it specifies the prefix uniquely as long as the adversary cannot find hash collisions. Okay, so for this hash function, like for leader election, we're just going to assume it's random and unpredictable. So, every time, every epoch, you call a hash function like, SHA-256, it gives you a random leader. Okay. So let me right now tell you the protocol, right? I'll write down a more formal version. And then maybe you can ask questions. I'm pretty sure that there'll be questions, right? So essentially, like I said, the protocol goes propose, vote, propose, vote, propose, vote. So the epochs will advance, right, for each epoch. Also, just another small thing, right? If I'm deciding leader like this, I'm assuming that the players are numbered from 0 to n-1. Okay, so we go epoch by epoch, and each epoch, the first thing you do is that the leader of the epoch will make a proposal. And this is what happens, right, at the beginning of epoch E, right? The epoch's leader LE does the following. It will find the longest notarized chain it has seen. If there are multiple longest notarized chain, you can pick any of them, right? So let chain be the longest notarized chain.
Notarized means finalized, right?
Notarized doesn't mean finalized. So let me, yeah, this is like a little bit circular, but notarized means that every block in the chain has gained votes from 2/3 of the people. So I will also explain notarized, but let me write this down first. Okay, so notarized and finalized has a slightly different rule. Like you have to be a little bit more patient. So you'll see that. Okay. So I will look for the longest notarized chain. And I have seen, right? So let's say LE has seen. And let H be the, the hash of the chain. Okay, so I want to build a next block on top of chain, right? This will be the parent chain, and that's why I'm computing its hash. And then, and now let TX be the set of unconfirmed transactions. So these are the transactions I want to put in the block, right? So now I will just essentially, I will sign a new block extending from the parent chain, denoted chain, and I will send the proposal to everyone. So I'm using this notation to denote signature. Right? So this is my signature notation. It means the leader LE has signed this message, right? And it's sending the message as well as the signature to everyone. Okay, and then essentially this block essentially extends from chain because it contains like the hash of chain, right? So it specifies exactly which parent chain I'm extending from. So as Junxi was asking, right? So one thing I didn't define yet is like notarize. So what does notarize mean? A block is notarized if it has collected votes from 2/3 of the players, and I'll explain what a vote is, right? A notarized block is if it has collected votes from at least 2/3 players. Maybe I can write 2/3 n. And notarized chain is like if every block in the chain has been notarized. Okay, so that's proposed. And then the next thing you do, like, is the most obvious thing. You are going to vote. And then what do you do when you vote, right? So during epoch E, every player does the following. Every player I does the following. I will wait to receive the first proposal from the current epoch's leader, right? So upon receiving the first valid proposal, from this epoch's leader LE, I will vote for the block, but with an extra check. I'm going to check one thing, and then if the proposed block looks reasonable, I will vote for it. And what is this thing that I check? I want to make sure that the block is extending from one of the longest notarized chains I've seen. Like it's not extending from something really short, right? Because for instance, if the proposed block is extending from a really short chain, like maybe then the proposer or the leader like is malicious and it's trying to throw away like a lot of the work we have done in the past. So in that case, I won't be happy with the block, right? Okay, I will insist, vote for the block if and only if it extends from one of the longest notarized chains I've seen. And what is a vote? I mean, a vote is simply just a signature on the block. So basically to vote for a block simply sign the block and send it to everyone. Okay. Okay, so we propose vote in every epoch. And then, so, one question that Junxi asked, okay, so when can I finalize a block, right? Does notarize mean final? So it turns out in this protocol, notarize doesn't mean final. You have to be a little bit more patient. So when can I finalize block? Let's look at this somewhat cute finalization rule. I want to look for a good pattern. So what is a good pattern? I will write down the rule first and we can go over an example. Okay, so the rule is I will look at all the notarized chains I've seen. And if I will look at the epoch numbers contained in the blocks. And if I ever see 3 consecutive epoch numbers, I can chop off the last one and the entire prefix is final. So we'll see an example, right? So right now, let me just write it down. Upon seeing 3 adjacent blocks in a notarized chain with, I want consecutive epoch numbers. Consecutive epoch numbers. So if I see this good pattern, I can finalize the entire prefix up to the second of the 3. Okay, so the best way to understand this rule is to look at an example. So let me draw an example, right? So first we have Genesis, I mean, obviously, and then let's say that the number in the block is denoting the epoch number, right? So let's say we have 2, 6, 7, and 8, and say every block in this chain is notarized. So now I will look for a good pattern. And in this case, I do see a good pattern, right? Because I see 6, 7, 8 appearing together. They're adjacent and they have consecutive epoch numbers. In this case, I will chop off the last one. So 8, in this case, 8 is not final yet, but the entire prefix is final, right? So in this case, let me draw that this is final. So again, like this whole chain needs to be notarized for me to apply this finalization rule.
Just to clarify, like if there is even one notarized chain with this property, we can finalize it. It's not
actually, your voice is very soft. Do you mind moving closer to the microphone?
Is it better now?
Yeah, now it's better.
Yeah, I was asking, like, I just wanted to clarify whether, like, if even one notarized chain has this property, can we finalize, or do we need all notarized chains to have this property to finalize?
One, so any notarized chain, like in
Okay.
my view, I'm running this protocol. I have a local view of like, all the notarized chains I've seen. If any of them has this property, I can take that chain and finalize all the way to like the last, the second of the 3, right? The triplet that has consecutive epoch number, I'm going to throw away the last of the triplet and finalize the entire prefix.
Okay.
So this, yeah, actually, now it's actually a good time to ask questions, and there should be questions. So like we are going to do the consistency proof together. So let me mention that, like, for instance, if you see, another example is like, if you see this. So let's say this is not at the end. The same applies. Like in this case, you can finalize up to here too. Like the triplet doesn't have to be at the end, right? It's like, I mean, if this is a notarized chain, then any prefix is a notarized chain too, right? If something is a notarized chain, then any prefix of the chain is a notarized chain too. So in this case, like, there's 10 at the end, but I still see a good pattern here, 6, 7, 8, and I can finalize this prefix.
So here, if the prefix is finalized and then when I'm building a block, should I go after 10 or?
Should I what? Sorry, should I?
So like if I'm proposed for a next block, then I should build it after the block 10.
Yeah,
right?
so if you are the proposer, if you're the leader, you take the longest notarized chain, not the longest finalized chain, right? So this is the longest notarized chain, and you take that and you propose the next block. Like here's where you put your next block here.
Okay.
Mm-hmm. Okay.
Also,
so,
in the abstract model we had constructed during last class, there I don't think it directly allowed for multiple chains. So will we say we'll only consider chains in that model which are finalized?
Yeah, only the finalized chains are output. So like in the abstract model we defined last time, in every round, the player will output some chain, right? You don't output the notarized chain. The notarized chain is an internal state of the protocol. When it becomes finalized, you output it, and then you can only you should only confirm transactions contained in the finalized chain. Not in the notarized, like that's not really final yet. So your transaction may still be undone if it's notarized, but once it becomes finalized, it can never be undone. And it's safe to output it. And this is what we are going to prove. Like why, is it safe to finalize when this good pattern happens?
Is there any reason we choose 3 adjacent blocks?
The 3, so for this particular protocol, like 3 is what we can prove. Like you can make it 2 if you add like a couple more instructions to the protocol. Like so this is like a kind of like a family of protocols. And when we wrote down this protocol, the objective we had was to make something as simple as possible and as natural as possible, meaning like with as few instructions as possible. Like in some sense, like right now, if you look at the protocol, it's like really natural. It's just propose, vote, propose, vote, propose, vote. I never have to like, wait for delta rounds. I never have to skip any round, like, right? So like if you are willing to introduce like some additional instruction, like, okay, wait an extra delta round here, you can improve the protocol like to like instead of 3, you can have a constant of 2. But that's kind of like not the point of this lecture. Like I want to show you one really simple protocol and prove it together with you, and then and that's what consensus should be like. Like simplicity goes a really long way when you try to implement these protocols in practice. Like I worked with engineers who actually implemented consensus, and that's like, there you really want it like simpler and simpler, so you can like explain it really clearly, and you also want to make sure like there's no way to misinterpret it, right? So like partly this protocol is cool is like because essentially in some sense I cannot think of any way to misinterpret it, because the most natural way to understand it should be the correct way, like as written, like okay, so let's so we are going to kind of discuss this finalization rule more, right? Because we're going to do the consistency proof. So in some sense, this is like a little bit magic, and partly, as I said, classically we had all these protocols, PBFT, Paxos, the entire family of protocols, and these protocols, I didn't talk about them, but the way they work, roughly speaking, is they also have like a propose vote, normal path. So the normal path is actually fairly simple. It's kind of like what I talked about. But what's complicated about these protocols is that the normal path, in some sense, doesn't give you liveness. And when the normal path fails, you have to fall back to a really complicated recovery path. So the protocol is like by model, it has 2 modes of operation. There's a normal path, which is fairly simple and natural, but then there's a complicated recovery path, and that's like the part that's confusing and difficult to understand. But in comparison, something like Streamlet is just a unified paradigm. Propose, vote, nothing else. There's no separate recovery path. And partly why we can do this is because, you know, there's some kind of a little bit of magic in this finalization rule. Okay, so what this finalization rule actually guarantees is the following, right? So we can stick to this example. So we have 6, 7, 8, and let's say, okay, so this actually can happen, right? Let's say all these blocks are notarized. So it's possible that, you know, at this height, there are 2 blocks notarized, but the finalization rule guarantees if you see 3 consecutive, then there cannot be any blocks notarized here. So this is not possible. This block can never get notarized. And that's what we will prove, actually. So first, let me quickly explain why, you know, you can actually have some block notarized here. And so this is actually possible, but this is not possible. So the reason why this is possible, you know, let's imagine, like when this leader proposed 6, the network delay suddenly become, you know, everyone received the proposal and they voted for the proposal, but the network delay suddenly becomes very long. So when this honest person wants to make a proposal, it hasn't received the notarization for 6 yet. So that's why, you know, it's building the block from 2, but then the network suddenly healed, right? So now all the votes suddenly get delivered. So then when the next person proposes, like it has received all the votes for 6. And in this case, like, you know, it just picked 6 to, let's say it picked 6 to extend from. It could be when this person makes a proposal, it hasn't received votes for 3 yet, but it has received the votes for 6.
How can it be that it's epoch number 3 after like 6? Like the person who's proposing the chain with epoch 3, it has to be before the person who proposed the chain with epoch 6, right?
Yeah, so let's imagine, let's like go in temporal order, like we can go step by step. So first, everything's normal up till here, but when the block, okay, so everything is normal, and then 3 starts to make a proposal. The leader of epoch 3 starts to make a proposal, and at this moment, I mean, obviously, all of this doesn't exist yet, right? So what will this leader do? It sees 2 notarized, so it will propose a block building on top of 3, and it sends the proposal to everyone. So all of you received its proposal, right? So you're going to vote on this block. But at this moment, the network slowed down for everyone. Like there's some kind of you know, DDoS attack or internet had an outage. And even though you sent your votes, like the votes are in flight, they, you know, it takes forever for them to get transmitted. Okay, so now let's say the leader of epochs 4 and 5, they just crashed and they never made any proposal. And now the leader of epoch 6 comes and, you know, it wants to make a proposal, but all these votes for 3 haven't been delivered yet. So 6 has only seen 2 notarized. So naturally it takes the longest notarized chain it has seen, which is this, and it builds the next proposal on top of 6. And people will still be willing to vote on 6 because they also haven't seen 3 notarized yet, because these votes are taking forever to deliver, right? So maybe like when the network, like, you know, is acting up, it could be like, you know, this person's proposal got delivered before all these votes get delivered. I mean, there's no guarantee that the delivery is going to be in order. Like, you know, something you send later in wall clock time can actually get delivered earlier, right?
But you're also saying that the block 3 has been notarized. So there are at least 2 by 3 players who have 2/3 players who have agreed
But-
to vote on it.
Yeah,
So
it has
been
when they
notarized.
see the block 6, like why would they vote on it? Because they've already seen a longer notarized chain.
It has
No, it's
been notarized, but
notarized.
all the votes are in flight. They're being transmitted. So I haven't seen it. I have no knowledge of what packets are being sent on the wire.
When you say you're
think-
saying node 3?
No, I think the notarized
node-
is. Well, just make sure the notarized is not when you see it and when you vote for it. It's when you receive 2/3 of the vote.
Yeah,
So
notarized
like
is a
the
local
first step
decision.
is you send the vote to notarize it. The second is you receive 2/3 of the vote from other people, and by that time, it will
Yes.
notarize.
When will the other people know that it has been notarized?
So notarized is a local decision. I know it's notarized when I receive the votes, and you know it's notarized when you receive the votes. And we may not have consistency. It's not like, let's say at time t, if I know this block to be notarized, you know it too. Because if we have that, we already have consensus. Like the problem has been solved, right? So we don't actually have like consistency regarding whether the block is notarized. So one thing actually, what I want to say is, there's an implicit assumption I'm making, which I didn't actually state it explicitly. Like there's, so I'm going to assume every time I receive a fresh message, I will send it to you. Like I will just send it to everyone. So this means as long as network conditions are good, if I see something now, you'll see it, 1 second later, like during periods of synchrony, during times when network conditions are good. So, but this doesn't guarantee simultaneous, right? It doesn't mean I see it now, you have seen it now too. Like if I see the block notarized, it doesn't mean you have seen it notarized, because if we had that, then the problem would have already been solved. So in some sense, the consensus problem is really just to overcome that delta rounds of difference. If it's like delta is equal to 1, it's just to overcome that 1 round of difference in view, right? Because we can easily guarantee if I know it now, every honest player will know it in the next round. Like even like, let's say the Don't Left Strong protocol was a little bit like that too, right? If I know it now, you'll know it in the next round, but that doesn't automatically give you a consensus, because consensus says, we are going to take a decision now, in Don't Left Strong, the protocol ends at T rounds, and we are going to take a decision now, and then we have to all agree, right? Okay. So I'm going to assume whenever an honest player sees a fresh message, it just echoes the message to everyone else. Whenever an honest player okay.
When you say whenever sees a fresh message, do you mean like receive any kind of message is going to echo? Will that be an infinite loop? Because if I see it, then I echo it to other people, and then they see my echo, they echo back.
Yeah, you only echo it once. So actually implementing these protocols are like, so this is something you need to like, when you implement the network layer, like you need to make sure that something like this is guaranteed. Oftentimes you don't want to implement it exactly like this, but the network layer essentially needs to guarantee this. Of course, you don't echo like duplicate messages. If you have echoed it once, you don't do it again. So in fact, guaranteeing this in a practical implementation is slightly tricky, because you have to think about, okay, if my node actually crashes and comes back online, like what do I do? Okay, so let's not talk about how this is implemented in practice, but maybe you can think about, if I asked you to implement a consensus protocol like Streamlet, like how are you going to take care to make sure that this is guaranteed? So this should actually be part of the network layer in the implementation, and not part of the consensus layer.
sorry, I still have a question for the blockchain with 2 branches. So say, so is this like a local version of someone's in some, let's say in some party's local version, this is the notarized chain I've seen.
Yeah, it's local, right? Everyone's making local decisions. I don't know your view. I only know my view.
Yeah. So like, let's say I received the 6th epoch first, and then when I received the 3 epoch, it's not extending from the longest notarized chain I'm seeing, right?
I mean, the three is the earlier epoch, right? So first, let's start from the very beginning, and if there's some step that's not clear, you interrupt me then. So okay. I'm going to do it in temporal order. First, everything's normal. All of these epochs are normal, and then the 3rd leader comes in and it wants to propose a block. I mean, at this moment, obviously, all of these are not around because these are greater epochs, right? These are in the future. So the only thing I've seen is 2 notarized. So naturally, I will propose a block extending from 2. So I send this proposal to everyone. All of you receive the proposal and you vote for it, right? Because it's like, extends from the longest notarized chain you have seen. So you send the vote. And at this moment, I cut off all of your network. So your vote is being transmitted, like it's being queued at the router. So your votes are all on the router. They haven't been delivered yet. Okay, so now the leader of epochs 4 and 5, they crash. They don't make any proposal. So there's no block for 4 and 5. Now the 6th leader comes in. He wants to make a proposal, but all of your votes are still on the wire. They're being queued at the router. So leader 6 hasn't seen 3 notarized. So it makes a proposal extending from 2. Okay, so now, leader 6 has better network than everyone else. So his proposal got transmitted to everyone. Everyone's votes for 3 is still queuing at the router. So everyone hasn't seen 3 notarized yet, but they have seen 2 notarized. And they're okay with this proposal because it extends from one of the longest notarized chains they have seen at that time. I mean, even though 3 is actually notarized queuing at the router, they don't know it. So they are okay with voting on 6. So they all send their votes for 6. And, now 6 got notarized, and then the 7th leader sees 6 notarized and he builds his block on top of 6. And maybe eventually at some point, all these votes, get delivered, the network got healed, all these, got out of the router's queue, and everyone later on sees 3 notarized, but by then this chain has advanced, right? Because 7 was building on top of 6 and 8 was happily building on top of 7. So it can, in my local view, I can still see this notarized and all of these notarized too, right?
Oh, I see. Yeah. I understand. Thank you.
Okay. And notice that in my example, no one was even malicious. Like this just can naturally happen if the network is broken. Because as I said, we will prove consistency without any network timing assumption. This means the network can occasionally be bad, and like all these packets can just be queuing at the router, right?
I was thinking if an honest player seeing the node 7 but hasn't seen 6, or his network is especially bad, so like everyone else has finalized the 6 but he didn't see it, then what will he do? And he sees 7 already built based on 6.
Okay, so you are saying if, let's say let me just draw the partial view. So say it's like this, right? This is 6, not B. So now you are saying, okay, 7, the leader of 7 comes in.
No,
it hasn't
not,
been.
Yeah, it's not the leader of 7. It's a random player who didn't see 6 being finalized, notarized. So 6 is not notarized, but they see a node 7.
So you're saying 7 proposes this block, and then I
My
received this
network down.
proposal, but I haven't seen 6 notarized. Is that your question? So in this case, I will not vote for 7 because like the parent has not been notarized. Like it's building from a parent chain, and let's say, you know, I haven't seen any chain with this hash, or I haven't seen any chain, you know, that has like,
Okay, so
I haven't seen any notarized chain with this hash, so I will refuse to vote for it.
Okay, so if I refuse to vote for 7 because I haven't seen 6 being notarized, and but I've seen 7 being notarized already, then what should I do with the node 8?
If I've seen 7 notarized,
Yes.
you need to see every block notarized. I mean, so in some sense, if you see 7 notarized, you can assume the entire prefix to be notarized, but either behavior is fine. So because actually, if you think about it, if 6 didn't get notarized, you know, it could be I didn't see it, but it must be someone has seen it notarized, right?
Yeah.
So if I see 7 notarized, you can assume actually the entire prefix is notarized, but you know, it doesn't matter. Even if you don't assume, it's not like, even if, let's say, I mean, because I define notarized as being every block needs to be notarized, right? So even if you reject it, it's everything still holds. Like in this case, either way to interpret it is the correct way. So like that's why the protocol is like, you know, it's like the most natural ways to interpret it is all correct. Like there's,
because I'm thinking about if I missed one node being notarized. So if I missed the 6 to be notarized, will that like make a difference on me notarizing the following node? So if I missed the node 6, but I could still notarize the 7 and 8 correctly.
So the way to think about it is like, this can only happen like if the network conditions are bad, or if the leader is malicious, then this can happen. If the network conditions are good and all the leaders are honest, this can never happen, because, you know, I would have like, I would have received those votes very quickly within one epoch, right? If like the network conditions are good, I said the honest players can make a round trip within a single epoch. So, and if the leader is also honest, then like he basically sent the proposal to everyone, then like it should not be the case that I see 7 notarized, but I haven't seen 6 notarized yet.
Adversary could delay the message, right? Or adversary may even be able to delay the message for however long.
When the network conditions are good, it means honest players can speak to each other within 1 second. It means during that time, the adversary delays message up to only 1 second.
Okay.
So yeah, so we don't need to provide progress when network conditions are bad, and we don't need to provide liveness when the leaders are corrupt either. So later on, you'll see the liveness theorem says if network conditions are good and we have consecutive honest leaders, then you'll make progress. Like you have like, let's say 5 consecutive honest leaders, you'll make progress. And then because we are electing the leaders at random, you know, with constant probability, we have like, let's say 5 epochs, they're all going to be honest leaders, because the 2/3 of the players are honest, right? So if we pick a player at random with 2/3 probability, it's going to be an honest leader.
Got it.
And then for consistency, you know, I mean, what you said can happen when either network conditions are bad or if the leaders are dishonest, but consistency will not be violated because of this. Yeah. Okay. So these are very good questions. I think we kind of got a sense about what's going on. So we are going to prove consistency now. And in fact, the consistency proof is very simple. So like, I think let's keep all these questions in mind, and maybe we can revisit them after we could prove consistency. And I think at that point, your understanding of the protocol will have been a little better. Okay. So how do we prove consistency, right? Like I said, what we want to prove is that this block cannot get notarized. And let me call this block X. And if you think about it, if I can rule this out, then I have consistency, right? So I will just prove it for these specific numbers, but the proof can be generalized to any 3 consecutive epoch numbers. Like there's no reason why they have to be 6, 7, or 8. It can be like E plus 1, E plus 2, right? But just for simplicity, let me prove it assuming it's 6, 7, and 8. And so there's one small lemma that we have to prove first. And this is like what I call the uniqueness per epoch lemma. Okay, so what this says is that in every epoch, only one block can ever get notarized. Like it cannot be the case that I see some block notarized in epoch 5 and you see another block notarized in epoch 5. So that can never happen. Okay, so suppose that f less than n over 3, right? So throughout the lecture, we are going to assume the adversary controls strictly fewer than n over 3. Then for each epoch E, there can be at most one notarized block of epoch E in honest view. So whenever I say in honest view, I mean in the union of all of the honest nodes views. This means in the union all honest players' views. So in other words, it means it cannot be the case that you see block A notarized of epoch E, and I see block B, a different block of the same epoch E, also notarized. That can never happen. How do we prove something like this? So this actually...
It's the same as the visiting broadcast, right?
Yeah, I think, didn't we prove something like this earlier? Yeah, we proved this,
Yeah.
like remember we had this lecture on Byzantine broadcast without digital signatures. We already proved something like this, right?
Yeah.
Okay, so now you should be able to prove it yourself, right? So what was the proof earlier? It's exactly the same proof. Yeah, I already forgot about it. Thanks for pointing it out.
It's basically saying that if we have 2 nodes notarized, 2 like blocks notarized in the same round, then we would have 4 and over 3 votes, and we only have an over 3 malicious player. Then it will be impossible.
Okay, great. Yeah, so Jinxi has told us the proof, right? So imagine for some epoch, I will just draw it now. Like previously, I wrote down the proof, but let me just draw it now. So let's say 2 blocks both got notarized, right? So it means 2/3 of the people voted for the orange block, and 2/3 of the people voted for the white block. And let's say they are both epoch E. And we are going to look at this intersection. And these are the folks who voted for both the orange block and the white block, right? And this intersection size has to be at least n over 3, because there are in total only n players, right? So if this is 2/3, the orange is 2/3, and the white is 2/3, then the intersection has to be at least n over 3. But now remember that the adversary controls strictly fewer than n over 3. So we can conclude that there's one honest node in this intersection. So there exists at least one honest player in this intersection. And because this honest player voted for both the orange and the white, it has to be the case that the orange block is the same as the white block. Okay, so I'm just going to leave it at this because, you know, this is something we had already proven like a couple lectures ago. Okay, so now I'm going to use this to prove consistency. Okay, so let's revisit the example we saw earlier. So we have Genesis, and I will just use the same example. It's 2, 6, 7, and 8. So I will prove by contradiction, right? Let's assume something here got notarized. This orange block got notarized. So let's ask, okay, what can the epoch number be? If this orange block got notarized, what can its epoch number be? So the proof is like, suppose for the sake of contradiction, the orange block got notarized. Okay, so what can the epoch number be for the orange block? Can it be 6, 7, or 8?
No. We have
Why
6
not?
and 7 and 8 already.
Yeah, exactly, because 6, 7, 8 are notarized blocks in this chain, right? By our assumption.
Could it be 4 or 5?
Yeah, it could possibly, let's say, be 4 or 5. So it could be greater than 8, right? So let's, so the only thing I want to rule out here is that it cannot be 6, 7, or 8. And then we can divide it into 2 cases. So, okay, so I have proven, you know, by this uniqueness lemma, which I proved just earlier, right? By the uniqueness per epoch lemma, this orange block must have epoch number either greater than 8 or smaller than 6. Okay. So now I'm just going to divide it into 2 cases using this, right? So essentially, what are the 2 cases? Case 1 is like this orange block's epoch number is greater than 8. And case 2, its epoch number is like smaller than 6. So we will rule out each case one by one, but it turns out the proof is symmetric for these 2 cases. One moment, I need to charge the device. Okay, so essentially the proof is symmetric for these 2 cases, and we just need to rule out one of the 2 cases. So let's do case 1 together. And in case 1, we assume the epoch number is greater than 8. So actually, without loss of generality, I can assume it's 9, because like the proof is the same if it's greater than 9. So let's assume, so case 1, assume this block's epoch is 9, and I claim the proof is the same if the epoch is greater than 9, and you can check it yourself afterwards, right? Okay, so now we want to rule it out. Okay, so how do we rule it out? Let's look at this picture, right? So as I said, I'm going to pretend the epoch number is 9. Okay.
Basically, 2/3 of the people have seen 8, so the length is at least 5. But if you build it after 3, then the length is only 4.
Yeah, you're almost
at least 2/3 of the people will not vote for this.
Exactly, and you almost gave away the proof. So we can do it a little bit more carefully, just slow down a little bit. So I'm going to present a slowed down version of the proof that Jinxi mentioned, right? So what is the slowed down version? The proof is like 2 or 3 sentences. So many people have voted for block 8, right? Because 8 got notarized. So that means more than 1/3 honest players voted for 8, and honest players only vote for this block 8 in epoch 8. And because more than n/3 honest players voted for this 8 block, it means they've seen 7 notarized in epoch 8. So now for all these honest folks who have seen 7 notarized in epoch 8, I'm going to ask you, are they going to vote for this orange block in epoch 9? Note that all these honest folks have seen 7 notarized in epoch 8, and that's why they voted on 8, right? Okay, so let me do it step by step. And then for convenience, I will draw the picture again so you can see it and the proof at the same time. Okay, I will draw this as an orange block, just as before. Okay, so the proof says, so first we know that 8 got notarized in the honest view. This means strictly more than n/3 honest players voted for in epoch 8.
More than O/3 or 2n/3.
So that's a good question. So why did I write this here, right? Because so we just need 2/3 votes, but the adversary can control, you know, less than n/3. So among these 2/3 votes, let's say F of them can come from corrupt players, but we know F is strictly fewer than n/3. And therefore, among the 2/3, you know, batch of votes, how many of them have to come from honest players, right? It needs to be strictly greater than n/3. If it's not strictly greater than n/3, there aren't enough votes, right? Okay. So this means, so let's call this the set S of honest players, right? So now I'm going to claim the set S has seen 7 notarized in epoch 8. And why is this the case, right? I mean, this has to do with the voting rule. Like I'm not going to vote for the block unless the parent is notarized. Remember, the voting rule says I will only vote for the block if it extends from one of the longest notarized chains I've seen. It implies the parent has to be notarized for me to vote on it. Okay, so the point is, okay, now we know that many honest players have seen 7 notarized already in epoch 8. And the question is whether the set S will vote on 9 in epoch 9. Will the set S vote for block 9 in epoch 9?
No.
No, they won't.
And why? Yeah.
Just they would only vote for the blocks that extending the longest notarized chain of saying.
That's great, right? So exactly. So as Ke and Jinxi said, you know, S will not vote for 9. 9 is the orange block in epoch 9 because it doesn't extend from one of the longest notarized chains they've seen at the point. It doesn't. Okay, so there we go. There we have our proof, because if so many honest players refuse to vote for it, then that block cannot gain notarization. Because for it to gain notarization, we know that it has to collect 2/3 votes. And you know, if more than n/3 honest players refuse to vote for it, then there aren't going to be enough votes, right? So very simple calculation, which says 9 cannot get notarized. Nine cannot get notarized in honest view, essentially. Okay, so that's case 1. And case 2 has like an almost symmetric proof. So without loss of generality, we can assume this orange block has epoch 5, because if it's smaller than 5, all of the same proof would still hold. And I claimed earlier that if the orange block has epoch number greater than 9, all of the same proof should still hold, and you can just like check for yourself. So now what about case 2? Like, how do we rule out case 2?
If this orange block got notarized, then the chain above the 7, 8 blocks would not be notarized.
So let's do it step by step, right? So let's suppose 5 got notarized for contradiction. So what does this mean?
5 got more than 1/3 honest votes.
Yeah, exactly. 5 got more than 1/3 honest votes. And what does this mean? Like, let's say more than 1/3 honest players, they voted for block 5 in epoch 5. So what must have they seen in epoch 5?
They've seen node 3 being notarized.
Exactly. All these people who voted for 5 in epoch 5 must have seen 3 notarized in epoch 5. And because they've seen 3 notarized in epoch 5, the question is, will they vote for 6 in epoch 6? Yes or no. So if I've seen 3 notarized in epoch 5, will I vote for 6 in epoch 6?
No.
Suppose I'm honest. No, right? So now we can conclude many honest players will not vote for 6 in epoch 6, and therefore 6 cannot get notarized, and this leads to a contradiction. Okay, so I won't write it down. The proof is in the textbook, and it's essentially symmetric. Okay.
So where did we use the fact that 6, 7, and 8 have to be consecutive? Can they be like 6, 8, and 10?
Great question. Where did we use it's consecutive? We used it because like when we divide it into 2 cases, we said it's going to be, so there are a few places that we implicitly use it. So first, we divide it into 2 cases, right? So let's use your example and see where the proof breaks. So what happens if it's like not 6, 7, 8, and it's like 6, 7, 10, right? If it's 10, I mean, this block can be 8. Okay. If this is 10 and this is 8, would the proof still hold? Like, you know, remember we are saying, okay, many saw 8 notarized in, many saw 7 notarized in epoch 8, right? So if this became 10, then we can only conclude many saw 7 notarized in epoch 10, and this will not rule out these people voting for 8. So let me just draw it separately, just to avoid confusion, right? So this is a really good question, right? So why does the proof break if it's like this? So in other words, is this possible? So this is actually a possible scenario. I can convince you in 2 different ways. First, I can convince you why this is possible. And second, I can convince you why the proof breaks, right? So let's first see where the proof breaks, and maybe that's the easier part. The proof breaks because earlier we said, okay, many people have seen 7 notarized in epoch 8, and we use that to rule out this block 9 from being notarized, right? But now that doesn't hold anymore because many people saw 7 notarized in epoch 10, and that doesn't prevent them from voting for 8 in epoch 8, right? Because, you know, I may not have seen 7 notarized in epoch 8 yet. So I will still vote. I'm okay to vote for this block if I haven't seen 7 notarized in epoch 8 yet. Does that answer your question? Was that Ankush?
Yeah, that's me. That makes sense. Thanks.
Great. Okay, so and then the other way to answer the question is this scenario is actually possible. Like you can create such a scenario, let's say when the narrow conditions are bad, for instance.
I think like the worst scenario is you have 2 parallel chain, which is like 1 like 5, 6, 7, 8, 9, 10. And
That's
here,
an awesome
like,
observation.
Yeah, like the thing we have here is once a chain is finalized, then all the following blocks can only build on the finalized chain. Is that what we proved here?
Okay, you're asking multiple questions. So first, I want to comment on your example. So your example is this. So this is actually possible. This is possible. It can happen. But in these cases, we don't finalize any blocks, so it doesn't violate consistency, right? So in your homework, I like your example. So in your homework, you will tell me why this scenario is possible. Like show, like let's say that when the narrow conditions are bad, it's possible that both of these chains get notarized in honest view. But that's the next homework, not this one. I'll try to keep that in mind and put it in the next homework. And
the second
what is the second
thing is, it's so basically we prove that once a chain is finalized, then all the following blocks can only build on the finalized chain.
Yes, exactly. You're right. Yeah, because
that's what we showed.
Yes.
Okay.
I mean, you could build elsewhere. So it's like, I guess once it's fine, okay, let's see if that's correct, right? So if it's finalized, let's say this is finalized, it means many people have seen this notarized, let's say in Epoch 8. So now in Epoch 9, going forward, like, are they going to, so first, they're not going to vote for anything that's here or earlier, right? So anything that's shorter, they won't vote for it. So they are only going to vote for anything beyond this point. But because there's only one block at this height notarized, anything they vote for after Epoch 8 must be like essentially a descendant of this block. So that confirms what you said, yeah.
Yes, okay, okay.
So we are actually running a little bit late. And I have to run to this Scilab Partners Conference. In the next lecture, we are going to talk about, so we can actually potentially even prove liveness together. So we are going to like talk about liveness together. And then I want to talk about, we have actually already learned the partially synchronous model, right? So far, you know, before Streamlet, like all the protocols we saw were in the so-called synchronous model, meaning, you know, if the narrow conditions are bad, we don't guarantee consistency. But actually for this proof, if you look at it a little bit longer, you'll notice that actually the consistency proof just holds regardless, even when the narrow conditions are bad. And when the protocol has this property, it's actually called a partially synchronous protocol. So in the next couple of lectures, the two things we are going to do, one is to talk about the liveness of Streamlet. And the second thing we are going to do is to show that in the partially synchronous protocol, we are going to show a lower bound on the resilience. Essentially, you have to assume 2/3 honest to get a consensus protocol in the partially synchronous model. So if there are n/3 or more corrupt players, then no protocol can reach consensus in the partially synchronous model. So that's what we are going to prove. Okay, so I will see you next Tuesday. Thank you very much.